it goes. Before we get into the couple of examples, I want to show you guys about calculating electric flux today, which is going to be related to the worksheet I just passed out. Hopefully it'll get to you soon. One announcement I want to make is that there's still one opening for a student research assistant in the atmospheric science project that is funded by NASA. Put that short. And so if you're interested in any atmospheric science, wildfire stuff, you know, how clouds form, why is the air so bad in the Central Valley, let me know, and we still have one spot open for that, and that's a paid position, so you get paid, I don't remember, like $16.50 or something like that an hour, up to 20 hours a week in the semester, and then 40 hours per week in the summer. And the summer also, you also are signing up to go to Maryland, where NASA headquarters is, for one trip for a week. So if you're interested in doing that, just let me know. So any science major is open to any science major, but specifically we tend to like people who have programming experience, because there's just a lot of data analysis that you have to use computer programs in order to analyze. But if you have experience with you know atmospheric chemistry, or how does the air quality affect the biology of not just us but other life around the Central Valley, that'll be good knowledge to have also, and we can teach you the programming stuff, right? Okay, so any science majors are welcome. So if you have any questions, just send me an email or just talk to me after class. Okay, so today we are the idea was for me to finish these examples yesterday, but as usual, I talk a little bit too much or struggle a little bit too much with OBS or this tablet, and so therefore we don't finish it. But yesterday we started talking about this idea of symmetry, right? There's different types of symmetry. There's translational symmetry, planar symmetry, where if something's a flat plane. Let's go back up to here, right? And there's also like spherical symmetry, there's cylindrical symmetry, and we're going to see a little bit of this in order for us to solve problems that may seem much more complicated, but we can simplify the math a lot by applying this idea of chemistry, and that's what this today's group worksheet is going to show you guys also. Okay, so when we did that, we also learned that, well, if we want to figure out, this is some arbitrary concept, it seems like, wait, why are we learning how to do this right now? It kind of seems like it's not useful. What we're going to do is actually combine this idea of electric flux with symmetry in the next section, which is the lecture for tomorrow, and apply it to what's known as Gauss's law in order for us to actually calculate either the electric field from a charge distribution that's much harder for us to do if we were to do it by hand using integrals, or actually sometimes impossible. Or you can actually, if you have the electric field, you can actually calculate the charge distribution inside some opaque box that we don't even know what's inside. So that's sort of an interesting way to study electric field and their relationship with the charge distribution that created them. But before we can do that, we have to have this idea of electric flux. Remember, electric flux is just pretend there's some electric field, or in this case there's some velocity field, okay, where the part of that field that passes through this rectangular surface, okay, that's the amount of flux through it, right? So if the surface, right, normal vector, meaning the one that sticks out perpendicular to that surface, is aligned with the electric flux, okay, that means the angle between them is 0, and therefore you actually maximize the electric flux, right? But if, in this case, where the normal vector, right, the surface is actually rotated, you can see that the flux actually doesn't pass through this little, rectangular ring, right, and therefore the flux there is 0. But in general, you can calculate this by taking the electric flux times the area of this surface times the cosine of this theta, where cosine of theta is the angle between the normal vector of that surface and the electric flux vector, okay? And this is where we came up to yesterday mostly, right? And since we have a cosine, right, and cosine tells you how parallel two things are to each other, and so does the dot product, right? The shortest way to write this electric flux formula, okay? If you have a constant electric flux and a constant area, okay, you can actually just take the dot product between those two vector values, okay? So this is if you have a constant electric field. So that's very important. And we're going to see an even more general version of this where you don't have a constant electric field, which will involve some integral and stuff like that, okay? So I want to go through this example that I didn't get to do yesterday, right? So let's say in an experiment, right, there's some constant electric field of 5.0 times 10 to the 4 newtons per coulomb in the I hat direction. So I'm even going to start drawing this. So I'm going to declare some x and y axis. Let's make my x this way, my y this way, my x this way. Okay. And since this electric field is in I hat direction, right, we expect it to go in the horizontal direction. Okay. So I'm going to draw that. So this is the setup of the problem, right? So we have some electric field that is constant. I can even draw it shorter actually. It might be more clear if I don't. Come on, erase. Give me the erasing. Okay, it's just slow. Okay. There's some electric field. Right. Right. The length represents the magnitude, right? The arrow represents the direction, right? Okay. So this is my electric field. I'm going to even write the formula over here. The electric field is actually 5.0 times 10 to the 4 newtons per coulomb in the I hat direction. Okay. Okay. And we have some disk that is where the normal vector is pointed in this weird direction, right? So it's pointed in the positive I hat direction, but negative in the j hat direction, right? So it's actually like pretend there's a little C. Yeah, you guys don't even know what a CD is, right? A DVD, maybe a DVD disc, right? That's pointed this way, so that's kind of like where my hand is pointed. Okay, and so we have some disc that looks like this, where the normal vector is pointed this way. Okay, right? And this area vector, right, is just the area of the disc times that normal vector, right? And that normal vector is pointed this way. Okay, so the area of a disk is just pi r squared, right? So pi r squared. And then the normal vector here, right, is 0.707 I hat minus 0.707 j hat. Okay, right? And the radius is given to you as, oops, right, 10 centimeters or 0.100 meter. Okay. Okay. So we can, since this is a constant electric field, we can apply that equation above in order to calculate this. Right, this is actually jumping to the solving part. Okay, so the electric flux, I think the book actually used lowercase e, that's fine. Okay, is the dot product between E dot dA. Okay, E, right, has an I hat component, 5.0 times 10 to the 4 I hat, right, dot product it into this more complicated vector, pi r squared, right, 0.707 in the I hat minus 0.0707 in the j hat. This is actually a unit vector. Okay, so when I take if I take the dot product between something that has I hat and I hat, right, those components are parallel to each other, right? So they just multiply into each other. Okay, so this is another way to do a dot product, right? So let's say you have A dot B, right? Right. So the dot product is actually the x component of x of A times the x component of B plus the y component of A. I'll write it in the right order. Times the y component of B. So that's another way to write the dot product, right? The other way is actually to calculate this angle between them, right? So if you were given the angle then I would do it that way. But since I'm giving this in the component form, I would just compute the component, right? Whichever way is easier, you want to do it that way, right? You don't want to do a lot of conversions between components and direction and angle form, okay? So in this case, right, this is the x component, this is the x component, right? So that's what this is going to be multiplying together, okay? So just 5.0 times 10 to the 4 times pi r squared, 0.707, right? And add to that, right, the y component of A, right? But is there a y component of the electric field? Yeah, if there's no y component, that means that magnitude, that component is actually 0, right? And anything times 0 is 0, so the second part of this is actually 0, so you don't even need to compute it. Okay? So if I plug in 0.1 meter here, and I grab my calculator, and hopefully you'll find the answer. Okay, 5 times 10 to the 4 times pi times 0.1 square times 0.707. Okay, so that flux happens to be 1,100. So we have 2 sig figs. Okay, and this is going to be in newtons times coulomb times meter square, right? Because electric field has units of newtons per coulomb, right? And the area has units of meter square, right? So the ending the SI units should be newtons per coulomb times meter square, okay? Okay. Any questions about this? Right. Yeah. So electric field has a direction, the area vector has a direction, right? But when you do two dot products together, this is also known as a scalar product. It turns two vectors into one scalar. So this is just a scalar. You don't have a direction on it, okay? Okay, that's a good question. All right, anyone else? Okay. So that's the simple case where we have a constant electric field and our little area is not moving around. But as you know, life in general, especially in physics, is not as simple. It can get a little bit more complicated if the electric field is not uniform, okay? So let's say I have some surface here. Let me just draw surface here. I'll zoom in a little bit, right? The electric field at this point is some electric field I, but the electric field over here is actually in a different direction. You can kind of see that it's pointing in a slightly different direction. Not just the direction, but the magnitude could be different between them, right? So in those cases, what do we do, right? As you can see, a lot of cases, electric field depends on radius, it depends on the coordinates, it depends on the direction, okay? So in this case, we have to go back to our calculus trick where what we want to do is actually calculate the electric flux on this little tiny bit, delta phi I, and then we have a little bit of electric flux, delta I j, okay? And the total electric flux, because these are just numbers, you just add all these numbers up together, right? So if I have an I add j, I can add k, whatever next letter, m, after j, right? K, you know, and all you have to do is just add up all these little tiny bits of electric flux, and then you get the total electric flux, right? The same technique we use to find electric field, right? Where we have a little bit of charge that creates electric field, right? And you just add up all the electric field due to those charges, right? An electric field going through a surface gives you a electric flux. If you have a tiny bit of electric flux here, tiny bit of electric flux here, tiny bit of flux here, if you add them all up, then you get the total, right? Just as the other case. So as usual, right, when you sum up all these little tiny bits of electric flux, right, it turns into the electric field at that particular point times a little bit of area, okay? And this is where, I don't know if they ever cover area integrals in calculus 2, okay? Where This is known as a surface integral, or calculating an integral over an area as opposed to along a line. Okay, so as you take the limit, as this delta area, a little bit of area, goes to 0, you turn this summation into an integral, right? The same trick we do with, when you take dx going to 0, it turns into an integral of dx. Okay, so the electric flux, right, turns into this dot product of electric field times a little bit of tiny pieces of area. And if you integrate this, then you actually get the total electric flux, right? As opposed to adding up a bunch of them, hundreds of them together. You can just compute an integral, because integral is just basically summing up a bunch of stuff together. Okay. So the same, I just want to connect this to a similar idea from General Physics 1, where remember when we calculated work, right? Let's say I have a object, right? I apply some force to it, okay? And I move it some distance, delta S, right? Right? If I want to calculate the work from it, what you have to do is actually take the dot product between the force and the distance that you moved it, this distance S, right? The translation, right, from 0, some S initial to S final, okay, right? And that's the dot product that's hidden inside an integral you have to deal with, right? In case of constant force, you can take this force out, right? If you have a constant force, you take this out, you're just integrating ds. Or if you integrate ds, that's just delta S, right? Very similar idea here, where we have this complicated thing hidden inside an integral that's going to be a mess to deal with, right? It's, it's not going to be an easy thing, okay? But this is the general form for calculating the electric flux on any surface that has any electric field that can be different at every point, right? And you just have to do this complicated integral between E and E dot dA, okay? So don't worry too much about it. I just want you guys to know that that's the general form. We're going to try to avoid that as much as possible, okay? Okay? Because there are certain surfaces or certain places where we can apply a lot of symmetry. That's why section 1 was important, so that we can actually compute this electric flux without doing complicated integrations of dot products, okay? So one example here is that, let's go down here, right? One example here is that, let's say, right, you have an electric flux. I actually don't like this picture that much. I'm going to draw my own, but I'm going to try to do the same color coding, where I have, let's say, a cylinder, right, like this, okay? And I know the electric flux, right, is kind of going, the electric field is kind of going along that surface, okay? It's kind of going, swirling around, okay? So the electric field is kind of going around like this also, okay? In that case, okay, there's two, I'm going to give you guys two different possible answers. Do you guys think the electric flux from this electric field through this cylindrical shape, is it 0 or not 0? How many of you guys think is 0? 1. Okay, how many of you guys think is not 0, or 2? Okay, great. We have some disagreement. That's good. Let's figure out which of you are correct. Okay. Remember, when you have a surface, the thing you care about, right? The thing you're going to do a dot product with is the normal to that surface. Okay. So I'm going to draw the normal to this cylindrical shape. Let's do that in green, right? So at this point, the normal is pointing this way. At this point, the normal is pointing this way. At this point, the normal is pointed this way. At this point, the normal is pointing this way. At this point, the normal is pointing this way. So is the electric field and that normal surface vector, are they parallel or perpendicular to each other? If they're perpendicular to each other, the dot product between two perpendicular vector has to be what? 0, right? So in this case, right, in these cases, the flux through those surface is actually 0. So you don't even need to calculate it, okay? Okay. So let's do the other case where, right, we have the same surface, but somehow, with my fancy charge distribution, I was able to make an electric field that points outward. Okay, so the electric field actually points this way, from the center, right? Right. Right, it points outward from it. So on everywhere on the surface, right, it's pointing outward from it. So now in this case, do you guys think the electric flux through the cylinder is it 0 or not 0 in this case? How many think it's 0? Okay, no one thinks it's 0. Good. Well, I shouldn't give the answer. How many think it's not 0? Okay, so hopefully everyone will think it's not 0. Okay, because once again, right, if I draw the little normal vector here, right, all of them are going to be parallel to the electric field, right? When you have two vectors that are parallel to each other, that actually maximizes their the dot product. Okay, so in this case, it actually comes out very simple because the electric flux, right, it's this fancy integral E dot dA. Okay, if we can think that, well, at every point on this surface, this electric field vector dotted into the area vector, right, this little n hat thing, right, since the magnitude of this is constant on the surface and little tiny bits of area, you can just get that so that their area is actually also constant, right? You can actually pull this little e out, okay, and you just have to do the integral over dA, okay? When you integrate a differential of something, it just turns that into that something, right? It just turns it into A, right? This is the case where we have the same electric field on that surface, okay? So to calculate the electric field, you just have, the electric flux, you just have to know the magnitude of the electric field, right? The area of the cylinder, right? Imagine you have a piece of paper. Can I just grab a piece of paper? Right? Right. So if I wrap it like this, it's a cylinder, right? If I want to figure out the area of this cylinder, I just unwrap the little piece of paper. I have to calculate the long edge, which used to be the circumference, right, and the width, right? So I just need to multiply the circumference times the width of this piece of paper. So that's just 2 pi r times the length of this, okay? And we're going to see this on our next example, okay? Right. Any question about this? So these are two special cases you want to look for, right? Because one, one of them is 0, which is nice. The other one, right, you have a constant electric field throughout the surface. The dot product between the vector is always pointing in the same direction, so the angle between them is always 0. Therefore, cosine of 0 always gives you 1. Then you can actually calculate the electric field the electric flux simply. Okay. So whenever you see a problem where you end up doing some crazy integral inside there, something probably went wrong. Okay. I'm not going to give you a problem that does that. Okay. Right. So there's the case where the flux is 0, and there's the case where flux is just the electric field strength times the area. Okay. So I'm going to do a quick example of this. Let's say we have a very long wire, right, with some charge density lambda, okay, and there's a cylindrical shell around it with a radius r concentrically, so meaning it's they share the same center, okay. The radius of the shell is r, the length is l. What is the flux through the shell, okay? So let's draw that. We'll set up the problem. Okay, so we have some wire, a very, very long wire, right? And we found that if you have a wire that's charged, it's going to produce an electric field that just points outward from it. In fact, the strength of that electric field is given by this formula, right? This is the electric field from a line of charge. So let's draw that. I'm going to draw not too many electric field lines, just for time's sake. Oops, I was supposed to go straight down. Okay, and then around this line, I'm going to draw. We have a little surface around it, even though I drew it very badly. Okay, it's supposed to be kind of concentrically around it, right? This is my little cylinder, okay, that has a radius r, it has a length of L. Okay. Okay. There's actually 3 different surfaces that we're talking about here, right? Since this is a cylinder, there's the top of the cylinder, there's also the bottom of the cylinder, and there's the sides of the cylinder, right? So I'm going to label the top of the cylinder 1, the bottom 2, and the sides to be 3. And we'll figure out what does the electric flux look like for all 3 of those surfaces, okay? Okay, so part of the setup, you probably want to find out what the electric field is, right, for a line of charge, right, which is this number, well, not this number, this equation, 2 times lambda. We're going to assume that the charge is positive. If the charge happens to be negative, we just have to make the negate the answer, right? And this is going to be going away from the line of charge itself. Okay, right? As I stated before, the area of a cylinder, right, is just 2 pi r times the length of that thing. Okay, and let's even put that n hat direction there, right? Okay, so if we want to calculate the electric flux, we go back to this formula, right? It's this complicated E dot dA thing. Okay, and hopefully some of it will be 0, some of it will be not, depending on which surface. Okay, those of you who remember maybe this is like 2nd semester calculus or end of 1st semester. One of the fundamental theorem of calculus is that if you have an integral over 3 different things, right? Integral is just basically adding up a bunch of stuff together, right? So it's the same thing as writing if I have the integral over surface 1, E dot dA, plus surface 2, E dot dA, plus surface 3, E dot dA. Okay? Where surface 1, right, is this cap of the cylinder, surface 2 is the other cap, right, and surface 3 is the body of the cylinder. Okay? So let's do a little voting. So this flux is either going to be 0 or not 0. So how many of you guys think that surface 1 is it going to be 0 or not 0? How many think it's 0? Still the same 3 people, right? Right. So both surface 1 and 2, the flux is 0. That's because if I move all these electric field lines out here, right, to the surface, right, you can tell that, right, the normal vector at the end caps are actually pointed horizontally, right? So the electric field is pointed upward, downward, you know, and outward, right? So it's perpendicular to the end hat factor, right? So this integral is actually 0, and so is the other one, right? So all we have to do is actually calculate one of the integrals, okay? And we're even not even going to need to do that, okay? So if we just try and figure out the flux through surface number 3, right? Since the electric field from a line of charge depends on the radius, right? On every point, like let's take this for example. At every point on this cylinder, it's the same distance from the wire, right? Same radius from the wire, right? Therefore, the electric field strength here is the same along the surface of the cylinder, right? You guys believe that? Each of these little dots here is the same distance from the wire, right? And the electric field only depends on how far you are from that wire, right? It doesn't depend on, you know, theta, right? Okay, so therefore the electric field is actually constant on surface number 3, right? If we did that, so we can actually pull out this electric field from the integral, and therefore, right? And then if you just integrate dA, right? Once again, that's just the area of that surface, okay? Right? Since n hat, right, is pointed in this direction, right? At every point on this surface, N hat also points in the same direction as the electric field. The dot product, well, you can say the cosine of theta, where theta is 0, right? This dot product just turns out to be the electric field strength times the area of that particular cylinder. The electric field strength up here is given to us, 4 pi epsilon naught times 2 times lambda divided by r, and we're just going to assume that lambda is positive for now. Okay. The area of a cylinder, as I stated before, is 2 pi r times L, right? Okay. And therefore, the r's actually cancel each other out. The 2 pi's cancel out with most of the 4 pi. The 2 even cancel each other out. So the electric flux through the entire surface, right, 1, 2, and 3, not just the side of it, is just lambda times, lambda times L divided by epsilon naught. Simple? Okay. Okay. So remember, to find out where the surface's flux is 0, just cross those out, right? Figure out where the electric field is actually constant, right, and points in the same direction as the normal vector of that surface. Then you can do this dot product, and then they just turn out to be the product between the electric field strength and the area. Okay? We're going to focus mostly on these problems that has the symmetry to it. Therefore, we can do these calculations pretty quickly, okay? All right. Any questions before we jump into the worksheet for today?